So very good day to everybody. Once again, this is electromagnetic fields and waveguides, and in today's class we'll discuss some practical sessions, especially with the reflex klystron. Actually, in the last class we discussed about cavity klystron. We'll discuss about reflex klystron. Then we discuss about TWT, traveling wave tube. Then about magnetron. Okay, so this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, once again, let me thank God for giving me this opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students and young researchers. Right. So in this class, we'll discuss about reflex klystron. What is the construction part of reflex klystron? How you'll illustrate the operation of reflex klystron. Then we'll discuss about TWT, traveling wave tube. Okay, the physical construction of TWT. The schematic electronic arrangement, electrode arrangement with the TWT. Then about the applications of the TWT. Then the third part of today's class will discuss about magnetron. So we'll discuss about cyclotron frequency magnetrons. What are the construction details of the cavity magnetron? What do you mean by fringing field? Okay, we'll try to understand the topic. Then back heating of cathode. You should understand that one. And we'll discuss about favored electrons as well as unfavored electrons. Then finally, we'll end the class with the phase focusing effect. Okay. So at regular intervals, I'll be giving you some short videos to discuss the knowledge in our topics. So this is reflex klystron. So it's basically a microwave generator. So that's a klystron that works on the reflections and oscillations in one single cavity. So that will be having like variable frequency. Okay. So here, if you can see, we'll be having electron gun that will be, emitting the light even. Okay. Then we'll have the anode cavity. Okay. RF out. We'll have the coaxial loop here. Okay. So here we'll be having the repeller space, repeller electrode to collect them. Okay. Then we have the potential VA, VR. Okay. So this is the anode potential and this is the potential with regards to the repeller. Okay, right. So generally a reflex klystron will be having the electron gun. Here we have an electron gun. Okay. Then we have this cathode filament. Then we have the anode cavity. Okay. And the electrode at the cathode potential. So that will be providing the low power and of course it will be having very low efficiency. So we'll go for the construction details. So normally this electron gun will be emitting the electron beam. So that one, it will be passing through this gap in this anode cavity. Okay, right. So the electrons will be traveling towards repeller electrode, which is at a very high negative potential. So because of this high negative field, the electrons will be repelling back to the anode cavity. So maybe when it goes to return, okay, so the electrons will be giving more energy to the gap and of course the oscillations are sustained. So it's assumed that the oscillations already exist in the tube and they are sustained by the operation. Okay, so the electrons which pass through this anode cavity will be having some velocity, some speed. Okay, so we'll have the operation of reflex klystron. So the electron beam is actually accelerated, okay, towards this anode cavity. So we'll assume that this reference electron ER, okay, reference electron crosses the anode cavity but has no extra velocity and it will be repelling back after reaching that repeller electrode with the same velocity. So what is there in the initial velocity? It remains the same, no extra velocity. So another electron, let us say EE, okay, so that has started earlier. So that is the reason EE, that has started earlier than this reference electron. That will be reaching the repeller first, but it will be returning very slowly. Okay, reaching at the same time as that of the reference electron. So both will be reaching at the same time. Now we have another electron which is late electron. Okay, late electron which starts later than the earlier electron and the reference electron, but it will be moving with greater velocity while returning back. So it is also returning at the same time as the earlier electron as well as your reference electron. Now, all these three electrons, earlier electron, reference electron, late electron. So, all these one reaching the gap at the same time, that will be forming electron bunch. Okay. So, this travel time, you can call it as a transit time, that will be having the optimum value. Okay. So, here we will be having, as I told you, the electron bunch EE, ER, EL. So, this is the repeller space. This is the position of the gap. So, we'll have this electron bunch over here. Okay. So, this voltage across the gap will be having positive, negative, positive, negative, positive, negative. Okay. So, this one will be having the bunching time. The total, okay, from here, okay, till this electron bunch, from the reference till the electron bunch, we have, 3 by 4. Okay. Right. So, that is considered as the one periodic wave. Okay. So, here we'll try to calculate the optimum transit time. So, the anode cavity will be accelerating the electron while going, and it will be gaining their energy by returning them during the return journey. Okay. So, when the gap voltage is at the maximum positive, so this actually lets this maximum negative electrons to retard. Okay. So, the optimum transit time can be given as T. Maximum optimum transit time is equal to N, an integer, plus 3 by 4. So, here if you can see, okay, so 1, 3 by 4. Okay, 1 plus 3 by 4. Okay, right. So, this transit time depends on the repeller voltage as well as the anode voltage. Then we'll have several applications. Normally, reflex klystron will be used in applications where there is variable frequency. Okay. So, here we'll be using it in radio receivers, portable microwave links, parametric amplifiers which requires parameters, okay, local oscillators, especially of the microwave receivers, and of course wherever we have like variable frequency, we can use it in the microwave generators also. Okay, so this is the application of the reflex klystron. Then we have TWT, traveling wave tube. Okay, so traveling wave tube, it's considered as the broadband microwave devices will be having no cavity resonators like the klystron. Okay, so amplification you can do it by prolonged interaction between the electron beam and the RF field, radio frequency field. Okay, right. So the traveling wave tube is actually a cylindrical structure. So basically a traveling wave tube is a cylindrical structure which will be containing electron gun. Okay, so that will be having the electron beam, okay, from the cathode tube. So it will be having anode plates, helix means some curve, okay, and then collector. So RF input is actually sent from one end of the helix and the output is actually drawn to the other end of the helix. Okay, so the electron gun will be focusing electron beam with the speed of the light. Okay, so here the magnetic field will be guiding the beam to focus without scattering yoke. Okay, so the RF field also propagates with the velocity of light, which is actually retarded by that helix. Okay, so helix, it's a very slow wave structure. Okay, so the applied RF field which is actually propagated in helix will be producing electric field at the center of the helix. Okay, so the resultant electric field due to this applied RF signal travels with the velocity of light multiplied by the ratio of the helix pitch to the helix circumference. So here if you can see electron gun, okay, we have this one cathode. Okay, so this is the input that is passed through the very slow wave structure. Okay, so this is the attenuator. Okay, and this is the collector to collect the signals. So the velocity of the electron beam traveling through the helix will be inducing the energy to the RF waves on that particular helix. Okay, so we will have this constructional features of the traveling wave tube. As I told you, electron gun, cathode, attenuator, helix. Here we get the input, here we get the output, and this is the collector to get the signals. Okay. So the amplified output is actually obtained at the output of the traveling wave tube. So here we will be calculating axial phase velocity. So it is given as V suffix P. So Vp is equal to Pc. Okay, we'll have with the case of collector. Okay, so pitch divided by 2 pi r. So 2 pi r is actually the total wavelength. Okay, 2 pi multiplied by radius. Okay, so here r is nothing but the radius of the helix. So as the helix is going to provide least change in this particular phase velocity, so it's preferred over other slower wave structures for the TWT. So in the TWT, the electron gun will be focusing the electron beam in the gap between the anode plates. So that will be going into the helix, okay, and that will be collected in the collector, okay. So it will be passing through this one, okay, to the collector, okay, right. So we'll be having this one. So electron beam will have the cathode, anode. So this one, it will be passing through inside, okay, through the helix, okay. Here we'll be having input, here we'll be having output, and it will be collected at the collector, okay. So we have the potential that is associated. So this is the schematic electrode arrangement in the traveling wave tube. So the anode plates, when at the zero potential, which means that the axial electric field is at the anode. So here the electron beam velocity will remain unaffected. Okay, so when the wave on the axial electric field is maybe at the positive anode, so the electron from the electron beam will be moving in the opposite direction. This electron which is being accelerated will be try to catch up with this late electron which encounters that particular node of the RF axial field. Okay, so at this point where the RF axial field is at the negative antinode, so the electron tries to overtake because of the negative field effect. Okay, so the negative field will be inducing, that will be speeding up. Okay, so the electrons will be receiving the modulated velocity. So as a result, in addition to the first wave, second wave will be induced in the helix. So the output will be larger than the input, and that definitely results in the amplification of the whole signal. Okay. So there are many applications of TWT, traveling wave tube. So you can use it in the microwave receivers as the low noise RF amplifier, and you can use it in wideband communication links and coaxial cables as well as repeater amplifier or maybe intermediate amplifier in order to amplify lower signals. Generally, traveling wave tube will be having longer tube life, so that's the reason they can be used as the power output tubes in the communication satellites. So continuous wave high power TWTs also are used in the troposcatter links as well because of the large power and of course larger bandwidths in order to scatter to the larger distances. And you can also use the traveling wave tube in high power pulsed radar and ground based radars as well. Okay, so we'll go on with magnetrons. So magnetrons are cross field tubes where you try to utilize the electric field and magnetic field, and both of them will be crossing, which means that they will be running perpendicular to each other. So here in traveling wave tube, even you can observe that the electrons, when you try to interact with the RF for a longer time than in klystron, will be having higher efficiency than the traveling wave tube. So the same technique you are going to follow in the magnetrons. So we'll have three types of magnetrons. One will have the negative resistance type. So negative resistance type between the two anode segments is actually used. It has very low efficiency and you can use it at the low frequencies like lesser than 500 megahertz. Okay, so then we'll have the synchronization between the electric component and the oscillating electrons is actually considered, and you can use it especially this particular type especially for the frequencies higher than 100 megahertz. Then we have the traveling wave or maybe cavity type. Okay, so the interaction between the electrons and of course the rotating electromagnetic field is taken into account. So high peak power oscillations are actually provided and you can use it in the radar applications. Okay, so then we'll go for cavity magnetron. So that's a type that you are going to use. So this magnetron, you can call it as a cavity magnetron because the anode is made into resonant cavities, and of course a permanent magnet is used to produce a stronger magnetic field where the action of both will make the device to work. Okay, so as I told you, the magnetron will be having a thick cylindrical cathode that is present in the center, and a cylindrical block of copper is fixed axially which acts as the anode. So the anode block is made by the number of slots that will be acting as the resonant anode cavities. So the space between the anode and the cathode, you can call it as the interaction space. Here the electric field is present radially while the magnetic field is present axially, okay, in the cavity magnetron. So this magnetic field is actually produced by the permanent magnet, which is placed such that the magnetic lines are parallel to the cathode and may be perpendicular to the electric field present between the anode and the cathode. Okay, so we'll have the construction details of this cavity magnetron, and we'll also have the magnetic lines of flux which is present axially. Okay, so here we see the construction details of the cavity magnetron. Okay, so we have the interaction space. Okay, that's where you have the cathode. Okay, and the copper anode block at the potential VO. Okay, so this is the coaxial line output. Okay, RF out. Okay, so this is the magnetic flux lines which are passing in the magnetron axially. Okay, this side. Okay. So the cavity magnetron will be having 8 cavities tightly coupled with each other. Okay, so the N cavity magnetron will be having N modes of operation. Okay, so the operation depends on the frequency and of course the phase of oscillation. Total phase shift around the ring of the cavity resonators would be 2n pi. Okay, normally like 2 pi means 2 multiplied by 180, 360 degree. So that multiplied by n number of modes of the operation. Okay, n is nothing but the integer. Okay, so if the phi v, the phase velocity, represents the relative phase change of that. So if this phi y, if this phi v represents a relative phase change of the AC electric field across the adjacent cavities. So here phi v, the relative phase change of the AC electric field, would be equal to 2 pi n by total n. Okay, so this n, as I told you, it's an integer. It can take 0, plus or minus 1, plus or minus 2, or so on, up to n by 2 minus 1, and up to final it would be n by 2. So which means that this n by 2 mode of the resonance can exist only if this n is a even number. So if n is equal to n by 2, so your phase change would be equal to pi. So the mode of resonance would be called as the pi mode. Okay, so n is equal to 0 means then phase change would also be 0. So this one you can call it as the 0 mode, which means that there will be no RF electric field, okay, between the anode and the cathode. So this one you can call it as the fringing field. Okay, which means that there is no RF electric field between the anode and the cathode, and this mode will not be used in the magnetrons. Okay, so this is the fringing field. Then we'll have the operation of the cavity magnetron. So when the cavity klystron is under operation, we'll have different cases. Okay, so we'll go one by one. So we'll have case 1, movement of electron when no magnetic field is present. So if the magnetic field is absent means you know B equal to 0. So which means that the behavior of the electrons will be having this one. So when the electron directly goes to the anode under radial electric force, okay, so we will be having, you know, the movement, okay, of the electrons. Okay, so this is the anode block, this is the cathode, okay, and this is the interaction space. Okay, so there will be movement of electrons, okay, A, when the no magnetic field is actually present. Then case 2, movement of electron when smaller magnetic field is present. So if there is increase in the magnetic field means, so the lateral force will be acting on the electrons. So that one, the electron B, which takes a curved path like this one, okay, with both forces acting on this one. Okay, same, okay, anode block, interaction space, cathode. So that will be a smaller force would be acting. So both forces would be acting on it. We'll get a curve. Okay, so movement of electron B when smaller magnetic field is present. So the radius will be calculating it as R is equal to mv divided by EB. So it will be varying proportionally with the velocity of the electron, and it will be inversely proportional with, inversely means it is actually divided, okay, inversely proportional to the magnetic field strength B. Okay, then we have case 3, third case. What is that? Magnetic field even further increase. Okay, so the electrons will be following a path, okay, such as electron C, that will be, you know, going across the anode surface and will be making the anode current to be 0. So this is where you will be getting the critical magnetic field BC which is the cutoff magnetic field. Okay. So here you will be saying from already we see here like this one curve. From there again it will take a curve like this, it will go. Already we have this one. So it will take like this and come. Okay. So this is the anode block, interaction space and cathode. So this is the movement of electron C when magnetic field is increased to more. Okay. So critical magnetic field. So here B is equal to BC. So magnetic field is equal to critical magnetic field. Okay. Then we have case 4. Okay. So if the magnetic field is made greater than the critical field, what happens? So B is greater than the critical field. Then the electrons will follow the path as this electron D, where the electron jumps back to the cathode without going to the anode. So that much high it is there. Okay. So that will be having, too much of heat if you supply. What happens? Back heating of the cathode. Okay. So from here it will go, instead of going like this, it will go and go out. Okay. So that's how the electron D goes out. So this is actually achieved by cutting off the electric supply when some oscillation comes. Okay, you immediately cut off the electric supply. So if this is continued, means the emitting efficiency of the cathode will get affected. So this is the problem. Okay. Then we'll understand the operation of the cavity magnetron with the active RF field. Okay, so we'll try to understand the operation of the cavity magnetron where the RF field is absent in the cavities of the magnetron staircase. Okay. So with the static case as like the traveling wave tube, let us assume that the initial RF oscillations are present due to some noise transient. So here the oscillations are sustained by the operation of the device. So there are 3 kinds of electrons emitted in this process. So that we can say A, B, C. So we saw that one. Okay. Case 1. When oscillations are present. So which means that the electron A slows down the transferring energy to oscillate. So such electrons that transfer their energy to the oscillations, you can call it as the favored electrons. Okay. So these electrons, you can be responsible for the bunching effect, just like the electron bunch. Okay. So case 2 will have electron B. Okay. So that takes energy from the oscillations and it will be increasing the velocity. Okay. So when this is done, it is going to bend more sharply. Okay. So that is going to spend little time in the interaction space and it will be returning to the cathode. So this electrons, you can call it as the unfavored electrons. So here the case 2, they do not participate in the bunching effect. Also these electrons are harmful because this one, since they immediately go to the cathode, it causes back heating problem. Okay. Then case 3, electron C. So that is emitted a little later, but it is moving very, very faster than the earlier cases. Okay, so it tries to catch up with this electron A. So the next emitted electron D tries to step up with A. Okay, so as a result, the favored electrons A, C and D will be forming electron bunch. Okay, as you see here. Okay, so or you can call it as electron bunch or maybe electron cloud. Okay, so this one you can call it as a phase focusing effect. So here we'll be having the electron movements in different cases, while the second case will be showing the electron cloud. Okay, electron bunches. Okay, so the electron clouds occur while the device is in operation. So the charges which is actually present on the internal surface of the anode segments will be following the oscillations in the cavities. So that will be creating the electric field which is actually rotating clockwise. Okay, so that can be seen when you try to perform the experiment.